All right. Working. Thanks for the introduction. Let's get started here. All right. We're going to start off with a quiz. So hope you brought your thinking caps here. Check under your chair real quick. Sorry, is this going in and out? Yeah. All right. Check under your chair. We got malware for you. All right. You guys see it? All right. Actually, we just have a file for you. We want to know, is this thing malicious? All right. Just want to know, is this thing malicious? Here's the hash. From this hash, can anyone tell if this file is malicious or not? Anyone, maybe? Well, all right, this isn't a good example. This is the empty file. Can't really tell. Fine, how about this one? What are we doing when we get a malware sample, maybe by hash, or an unknown binary sample, we get it by hash, deciding whether it's good or bad or not, right? First thing we do, this is really not the best clicker, I'm sorry. Look it up on VirusTotal, all right? Unfortunately for this one sample here, we're not seeing any results. That's making me think, well, maybe this is perhaps some kind of custom binary targeted at my organization, or maybe it's just the newest version of Windows Update that was just pushed out moments ago that VirusTotal doesn't have yet, right? All right, don't know what to do there. Next thing I do I look it up in IDA Pro? Hopefully not, because that makes my eyes bleed. I don't want to do that yet. Next thing I probably do is run strings on it. I moved to my basic static analysis techniques. I go from my most general tools to my most specific in order to save time and effort, all right? Run some strings on it. Here's the output here. Doesn't tell me very much, all right? I see the PE file header. I see some other sections and other strings that, you know, they look fairly legit. Standard section names here. We have text section, our data, data section. As I kind of scroll through here, I don't see anything that stands out. Things that I would be looking for are suspicious file names or network indicators that I could look up on various internet resources like domains. I can look at the registrars, things like that. Use that type of information to decide if a file is good or bad or not. Unfortunately, this output here, there's just nothing for me to look at. I don't know yet, right? And I can continue on my analysis here using more and more advanced tools. I can look at the PE file format, look at the imports, the exports, and use some of my background and experience to decide whether I think this file is malicious or not. If it's malicious, I can do additional analysis on it. But if I don't know, I'm in this kind of quagmire. I don't yet know what to do, and I can't go back to my client or my boss and say, hey, we've got a problem yet, right? So what do I have to do? Well, if I know how to use IDA Pro or WinBag, I can open it up and use these advanced techniques. But again, those tools kind of suck. If I don't know how to use those tools, they suck because they're complex and annoying to use. If I don't know how to use those tools, I have to deal with an annoying reverse engineer. They often smell bad. They speak funny. They listen to weird dubstep music, right? They're kind of annoying to deal with. They also cost a lot of money. Maybe I don't have access to one. And again, this is not a good situation to be in. We want to triage our binaries as fast as possible and decide at the earliest possible moment whether or not a file is malicious or not. The approach that we're tackling today here is with these strings, and in particular, obfuscated strings. We're here to introduce a tool, FLOSS, which automatically deobfuscates encoded strings within malware binaries using some pretty interesting advanced techniques that we're going to get into. So that's the overview of our presentation here. Stick with us here. We're going to get into some good stuff. Background, again, my name is Ballenthin. I'm on the FireEye Flare team. We're a small team of reverse engineers. We do most of the malware that comes into the entire FireEye organization. So we have a pretty good grasp on what's out there. But like probably many of you, I'm pretty lazy. I like to rather play computer games and listen to music than do my job, right? So I'm trying to make my job as easy and fast as possible and cheapest for my customers. So that's what we're here to talk about. You got your own. Great.
Hi, I'm Moritz. I'm also on the Flare team. I like traveling, and when I travel, I have ideas like developing this FLOSS tool. So, what do we often see? We always encounter new malware, and everyone's familiar with packers. What malware authors and even benign software often does is to hide or compress code, obfuscate it in that way, so you don't get to see the actual, the imports, the regular stuff you would expect from a binary. You get this packed file. And before the malware then runs, it unpacks itself, and then you get to see all the good stuff. What we often see is that this is not too common for like more targeted malware because it's pretty easy to detect once there's only one import, which is a virtual protect or something like that, to unpack. It's pretty easy even for common antivirus software to flag as malicious. So I already gave away this answer now, so you don't have to give it to me now. What we often see though is that strings and resources are encoded and obfuscated because that's still something that doesn't give away too much from a detection standpoint, but it hides the intent of the malware and it makes it harder for an analyst to find out what this file does. So the on-disk executable has obfuscated strings, and once the malware wants to use it, it deobfuscates them, uses them. This could either happen once the program starts and you do it right at the beginning for every string, or you just do it immediately before you use that specific string. We're going to go into an example in a little bit to make this more clear. And then after that, you could even deobfuscate it again. What strings would be interesting for this intent specifically? We're looking at command and control server addresses, so domains, IP addresses, which already give away a lot, for example, from a detection standpoint. Once we have those strings, domain names, we can look in our environment for communication to those. If we have register keys and file names from strings, we can find other samples in our environment. And from the dynamic imports, we can tell what this malware is roughly doing, maybe. So this is a good like in the middle. It's in the middle between completely packing the file and just having everything sitting open there, which can be easily analyzed. So the file appears normal. By that we mean the imports look good. It might be signed using a valid or stolen certificate. It's everything looks normal, but you can't tell anything from the strings. So how do malware authors actually do this? This is an example source code of a very useful program. It resolves this host name and returns 0. And once we compile this and look at the strings, we get everything basically in clear text. We can see there's a call to get host by name, and we see the domain name. We can then use this again to find traffic to malicious domains and other activity in our network. So as a malware author, one thing you could do is write this little decoding function which XORs every character of a string, and then you just put this obfuscated version into your source code. So instead of having the clear text domain name there, you have an encoded version. And then you run strings as an analyst on this, and you can tell, okay, there's a get host by name, but it doesn't appear to be a valid domain name or anything of interest to me. And even if you could tell, oh, this string might be encoded, you have no idea how it's encoded and how you can get to the original string. Ways to do this, there are a bunch of implementations. One way would be this is for malware authors. There are ways to do this. You can transfer the source code, so just run like your SAT or AWK on it, transfer the source code from the clear text, replace every string by the encoded version, and then do something we just saw in this example. You could also do it on the preprocessor levels by using macros, or during compilation time, for example, using Clang. And from a complexity standpoint, it's It can range from just a simple XOR, or you could have an RC4 encryption for every per string with a different key. So this is just to give you an idea. There's a million ways to do this, and it's very hard for an analyst to do this and analyze everything over and over again. Yeah.
So, for those people out there, have you guys dealt with malware before that does this kind of technique? Is this familiar to you, or is this like brand new? Okay, I've seen a lot of nodding heads. This is something I see on multiple times per week. When I'm reverse engineering, this is not some theoretical attack. This is what I see every single week, okay? So it's extremely common. There's a million ways to do it, and that's what Moritz was saying. So any time that we can win even a fraction of those samples, we're saving a lot of time, and we're solving real-world problems. So that's kind of our motivation here. This is something that's extremely prevalent. It's not a theoretical attack.
So it's annoying to reverse engineer. We know, most of the times we know this file is malicious, but we need to find those indicators for network analysis and host-based analysis. And it's also annoying for forensic analysts who just is looking at this file statically, using strings, using other tools, and it forces them to involve other experienced reverse engineers or have an expert system developed for millions of dollars. And we're trying to not make this happen. That's why we released this open source tool for free. So how do reverse engineers actually, how do I go about decoding functions, decoding strings that are obfuscated in malware? One thing you can do is you can debug the program, run it till its termination point. So before everything gets removed from memory, and then you dump the strings that are still in memory. You compare those to the strings you had before, running strings statically, and sometimes you get a win from that. Most often, though, strings are not really accessed. You have stack strings, for example. You have strings that get dynamically allocated and freed if the programmer knows what he's doing or she's doing, or if there's strings that get re-obfuscated after using them. An example for stack strings, the Flare team already provided a tool for this. It's on our GitHub. It's just you create those strings during runtime on the stack, and they never get. Well, they are in memory, but at the point of the program termination, you probably won't see them. So that's an issue. Another way to find those strings, you can find the decoding function in IDA Pro. You do your analysis. It takes some time to find those functions, and then you run the program's decoding function on all the arguments. So all the obfuscated strings, you try to run the actual code. This is most the correct thing to do. It uses the malware's code. You don't have to write code yourself. But the problem is it's very hard to find all the arguments and instruct the malware to do this for every, let's say there are 20 encoded strings and you have to instruct it to do this. It's very annoying, and even worse if the decoding function is inlined into the binary, then the difficulty goes up by a lot. Last thing we do, this is the most very flexible way. You can re-implement the decoding algorithm in Python or your scripting language of choice, and apply this to every instructed obfuscated data you find. It's very tedious to do this. It takes a couple of hours, and it has to be done over and over for every binary you find. So even if they just change a single character in the key, you have to re-implement it again, and very annoying. So here we go, FLOSS.
So can anyone guess what we're here to talk about today? Like, what problem are we trying to solve, right? Like, let's see if we can find a way to automate the extraction of these obfuscated strings so that on a weekly basis, I don't have to sit there and re-implement malware author's code in Python to extract these strings. It's just such a tedious process. I really enjoyed it when I was a junior reverse engineer. I thought that I was like doing really good work, and I was. But then by like the 5th time I did it, I was like, I'm so sick and tired of this. And now at this point, I'm on like my 500th sample, and I still can't reuse much of my code because every single sample basically has a different set of configurations, a different set of arguments that it passes to the decoding routine, a different way of setting up the stack. These are details I don't want to concern myself with. Let's find a way to automate that. So what we've got here today is FLOSS. FLOSS is the FireEye Labs obfuscated string solver. It's a tool that's going to help us, and we're going to give it to you here today for free. It's not yet under your chairs. All right? So FLOSS is a simple-to-use tool. What I mean by this is if you know how to run strings.exe, you know how to use FLOSS. This is good, right? It also takes a lot of hard work that's come from Moritz's brain, my brain. I've thought about a lot of these encoding routines, so has Moritz. We've come up with some pretty interesting solutions about how we can automate these techniques so you don't even have to think about this again. All right? It's going to solve many of the malware samples out there. It's not going to solve all of them, but if it solves 80%, even 50%, we're saving a lot of time. So let's talk about these techniques. All right? Going into a little more detail about how easy is this thing to use. Well, the first thing I want to mention right now, we just pushed it an hour or two ago to GitHub. It's not just a Python script that you download and then install a bunch of dependencies for and like wonder why it's not working. No, we've packaged it up for at least Windows and Mac as not Mac, I'm sorry, that's one we haven't done. Linux, Windows, just because we don't have Macs yet. As standalone executables. You go to GitHub right now, you download a single exe, you run it with arguments, it works. If you want to hack on the Python code, you're surely welcome to. It's pure Python. It's easy to hack on and understand what's going on there. So that's very easy to do. But if you want to run it, it's ready to go, out there. You get on GitHub. Sorry, yeah, go ahead. It uses some of these advanced analysis techniques. And we're going to talk about these in a lot more detail in the next couple slides. But some of the major takeaways are it uses solely static analysis techniques. Now, why is this important? Why do I mention this? How many of you guys have malware sandboxes out there? Then the rest of you guys should go buy FireEye, right? No, this is not the point of the talk, right? You can spend tens or hundreds of thousands of dollars on technologies. You can spend 20, 40, 50 hours building a virtual machine with all your tools in it so that you can run malware so that it doesn't connect to the internet and doesn't exploit the rest of your network. You can do all these crazy things. And that's in order to do things dynamically, right? When we're running malware dynamically, we can actually let it execute on the CPU and watch what it's doing. We're doing everything statically so that we have complete control of the malware, and unless there's some kind of crazy 0-day in python.exe, which I really hope doesn't happen, we basically don't have to worry about compromising our analysis system. So that's nice. It makes it very easy to use on many systems. And again, we'll dig into the techniques in a second here. Go ahead. All right. The algorithm. Let's dig into how this thing works. What did we achieve here? Go ahead. Essentially what FLOSS does is it starts with a set of heuristics that process the entire executable. It looks at all the functions, basic blocks, instructions, and it ranks those functions to figure out which one of those functions is most likely to be a decoding routine. This is probably the most one-to-one correlation between what's in my head and Moritz's head and what's in the code there. We used our experience, what we have most commonly seen in malware, to identify encoding routines. Then we translated that into Python code, and that's what we use. We find the decoding routines. Once we find decoding routines, we actually just emulate those decoding routines using all the data that's already in the malware to do the decoding for us. We don't have to re-implement things in Python. We don't have to dynamically use a debugger or anything like that. We just emulate the code using a fake virtual CPU and look at the effects of the malware as it attempts to execute its decoding function. Once we've emulated those decoding functions, we can simply look at the virtual state of that memory. We can look for strings in those, the effects of the instructions, and if we find anything, we can dump them out. It works really well. So the first step, as we go into this in a little more detail, is to analyze the binary on a high level. We look for all the functions, and we use a tool called InfoSec to do this. This is essentially a scriptable instance of IdaPro that's free and pure Python. It's a great tool out there. So we use it to identify all the functions. We use heuristics to process those functions and identify the decoding routines. Once we know which are the decoding routines, we look for references to those decoding routines. We figure out where in the malware is the author intending to call the decoding routine. Because when we know when he's calling the decoding routine, we just have to look around in that same area to find the data that needs to be decoded. The stuff that if we were to just run strings on the executable, we would just get gibberish. We wouldn't find anything. But that's the data that we need to isolate and find. Those are the arguments to the decoding routine. Okay? Once we've found those things, we can take snapshots of the CPU. We're kind of doing some emulation in the background here. We found the arguments. Then, once we know what those arguments are, we can actually pass them and emulate that decoding routine in a virtual CPU. When we're doing it in this virtual CPU, we have complete control over every instruction that's being executed and how the CPU handles it. Now, of course, there's corner cases here on like what happens if you have a divide by 0 or something like that. We ignore things like that. Most of the time, this works really, really well. Once we've emulated these decoding routines to their completion, for example, when the decoding routine hits the return statement, or maybe it falls into an infinite loop, and once we've executed, say, 100,000 instructions, we just say, okay, that's enough. We look at what the effects of that decoding routine are, and we can run the classical strings algorithm on it to dump out what we need. Does that kind of make sense? Yeah, it works great. I'm really excited by this tool here. Go ahead. All right, as I mentioned, we use this tool, ViviSec. If you are a Python developer, if you do reverse engineering or enjoy just kind of understanding how binaries work, this is a great tool to get started with here, ViviSec. It's free it's already on GitHub. It's been in development for like 10 or 12 years. It has a long history behind it, but it's still not as popular really as it should be. Some of the cool parts of it are that it allows you to do basically all the analysis that IDA does in a scriptable way. So again, finding functions, cross-references, strings, data, code, all these kind of things, easy to pull out programmatically. As a UI, we don't use it here. Other things that it has built into it, symbolic effect analyzer, code emulator, debugger, all these things packaged into one in pure Python. It's a great package. So that's what we use for doing the control flow analysis, identifying functions. And as I mentioned earlier, we have to identify the decoding routines. We use the plugin-based system to implement heuristics to find these decoding routines. And we use a plugin-based system because this is the #1 place where FLOSS right now currently fails. Okay? The place that it most currently fails right now is it's just not finding the correct decoding routine. Instead, maybe it identifies memcompare or some other short function that has a lot of loops to it and thinks maybe that's the decoding routine instead. So we have a plugin-based system that allows us to easily extend FLOSS and quickly fix bugs to identify more of those decoding routines. Now, one of the takeaways here is that we could emulate every single function in the entire binary and do a great job, and that would be the perfect solution. But that might take a while. It might take 5 or 10 minutes to do all that work. So by using these heuristics and more precisely identifying the decoding routines, we can actually achieve higher performance. But if we have a bunch of false positives, it's not a big deal. So the takeaway from that is that it's an extensible system. It's an effective, fairly optimized system. But again, we have a lot of flexibility in terms of using it. Heuristics that we found to be really effective are, for instance, can you hit the next slide? Oh, this guy here. Here's an example of the core part of a single decoding routine. All right, this is a screenshot from IDA Pro. It's a single basic block. We have a couple of, maybe 15 assembly instructions here. And the one that really catches my eye is right in the middle there. There's an XOR instruction. It's a non-zero XOR. We're XORing with, I think, a static key. What are we doing? We're using the hexadecimal byte 7 to XOR every byte in an array. We kind of loop through each one of those bytes and apply that XOR operation. We also do some arithmetic shifts. So one thing that our heuristics identify, that's a weird kind of XOR. You don't see that in normal code. Another thing we see, another interesting feature here, is this is a tight loop. When we get to the bottom of this basic block, there's a branch. One case falls through. The other one jumps around and goes to the same basic block over and over and over again, really, really fast. This is a tight loop, and this indicates to us it's kind of iterating quickly through an array. These are features we find really interesting and help us identify decoding routines. Okay? Once we've found decoder routines, our goal is, again, to emulate them. Okay? So we have this very effective virtual CPU and memory system. And what we can say is, okay, here's some data. Here are the arguments to this one function. Tell me what the effects are on the system after, say, 10,000 instructions. Or really, every time I hit a call instruction, pause for a moment. Tell me what the state of the system is at that point in time. and allow me to do my analysis and continue on executing. So that's what we're doing there. All right, that's our goal. In order to do this effectively, we need to know what the arguments are to the decoding function. So we need to do a bit more analysis on the binary, and that is to extract the arguments that might be passed to the decoding routine. I mentioned this earlier. The way we do this is essentially to brute force emulate the entire binary, to emulate every single instruction and every single basic block. And the reason we do this is we're exploring all the code in order to find all the possible arguments to every decoding routine call. Okay? At each call to a known decoding routine, which is what we found during the heuristic stage, we take a snapshot of the CPU and the registers and the memory at that point in time. We can, from that snapshot, extract the arguments to the function. It's kind of like taking a snapshot in VMware Workstation. It allows us to jump back and forth to different places in the program at different states. Okay? An example of this, real quick, is we can be emulating here, instruction by instruction, seeing what the effects of the system on the system of each one of these instructions. So we hit the test instruction. We have a branch here. Because we have a branch, we have two possibilities of where the CPU may go next. So we take a snapshot at this point of the memory and register state. We can now pick one of the branch destinations and continue emulating there. We do the XOR here, and now we have another branch instruction. So we can take another snapshot at this point. Now to make sure we're brute forcing, we're covering every possible basic block, we revert to our previous snapshot and go down the other branch. And in this way, we kind of breadth first, analyze all the possible basic blocks. And when we come to a call instruction, we can say, where are we about to jump? Is this a call to a decoding routine? If it is, let's make sure we extract the arguments that would be passed to the decoding routine so we can subsequently emulate with those arguments. Does that make sense? Sweet. All right. At this point, I know I've mentioned it a couple times. We do the emulation of that routine many, many times, once for each set of arguments. We expect the decoding routine to have some effect on the state of the memory, right? If it's changing all the bytes in an array, we can diff the state of the memory before the decoding routine and after the decoding routine and look for bytes in memory that have changed during that routine. It's a pretty quick operation. Once we know the bytes that are differing, we can just run strings in those differing bytes, and now we see what has been decoded within that function. I hope that also makes sense. It's pretty effective. All right, time for a demo here. It's definitely going to work.
Always works doing demos.
Point. All this that I just talked through is what we would be doing manually in IDA Pro and WinBag on a weekly basis. It was painful enough for me to try to explain it to you in words up here, let alone do it every other day. This is why we're trying to automate it.
I love you, Microsoft. So we run strings on this binary, and we get a bunch of output. I can't really nothing useful here. So a bunch of gibberish.
But if you were to pull it up in like PE view, or you look at the imports, you would see, okay, it has a bunch of normal imports, you know, kernel 32, maybe some kind of normal looking things. Maybe it is signed by someone, NVIDIA, you don't know if it's a stolen certificate or not. Don't really know if it's good or bad.
I only see half of
it. Cool. And now we'll run FLOSS on it.
Okay. So now we're running FLOSS. First thing it does, it's running its heuristics to find these decoding functions. And right now we analyze the top 10. So this is the listing of the top 10 functions FLOSS thinks are possibly decoding functions. And then we emulate those with the identified arguments. We can see here for this function, it actually found 30 strings. So we get some information. There's like almost a domain here. different stuff. Looks interesting, and it helps us in our analysis. There's a URL, and there's more strings giving us host-based indicators. And yeah, file names, anything of use to us. So that's one example. So this was running FLOSS on the whole file and analyzing every function. You can also tell it to just look at a specific function that you identified in either Pro or Vivisect or whatever tool. And you can just find all the arguments for that function and specifically analyze those. Takes about, well, it was pretty quick for this one because it's only looking at 8 strings that it needs to decode. Again, useful output, and I don't know if we've mentioned it yet, but those encoded strings are normally much more valuable than just regular strings you find. Once you get something out of this, it's like, okay, somebody tried to actively hide these strings, so they must be of some value. Domain names, file names, good indicators.
Right, and for a legit program, if you were to run a legit program through FLOSS, how many strings would you expect to see in the output? Probably 0. Like, why does a legit program have to hide any strings whatsoever? So simply seeing some output here might be an indicator to you that something's fishy going on. Just a thought.
Okay. I think there's one more demo. This warning message is totally normal. And yep. Yeah, and here we get some good network-based indicators. This guy's using Twitter as its C2 server, basically, and we get like ID fields and URL parameters, and yeah, takes about 11 seconds to run it for this. So that's the demo.
Yeah, so pretty neat stuff. Did you guys catch what he was typing on the command line there? floss.exe, path to the malware.
Can't see it.
And it just gave him results. Like that's our goal here. I've been to a number of conferences before. I've been to a lot of really interesting talks, and a lot of times at the end of the talk, the guy is basically talking, or the girl is talking about, I made this cool tool, I think you guys should use it. I'm excited to use it. I go to download it, I find it on GitHub, I have to compile it on Windows and get all these other libraries. And then I try to use it, doesn't work, I have to talk to him about it. I know how painful that is. So one of our goals here was to get something that worked, something that's kind of cool, you know, it could really save some time in some of our jobs, right? But we also want to package it for you guys to use right now. And so when I mentioned earlier, we packaged it as standalone executables. They're on GitHub this instant. You go, you download them. Moritz did that right before our talk and executed them.
Right here.
There's no more installation to it. If you want to install it manually, you can. You can use it right now. So I don't know. I'm pretty excited about that fact. I'm going to be using these executables, even though I do have the source. I wrote it myself. Sweet. So at this point, I hope we've kind of motivated you to understand. Let me do questions right at the end. We're just about at the end here. Why you might want to take a look at this tool, right? One, it's easy to use, and it incorporates some fairly advanced techniques, emulation, heuristics, binary code analysis that maybe you're not already familiar with. Maybe you are, and you just don't want to do them again. You can already do it in your sleep. You don't want to waste time on it. FLOSS codifies a lot of those techniques. It makes it easy for you to use them. It's pure Python, so that if you do want to hack on it, it's easy to mess around with. And we're happy to incorporate your changes. Adding new plugins that identify more decoding routines is going to be easy, and we can't wait to get those incorporated in. So I do hope you contribute there. But we will note that right now, our goal is not to solve every single encoded string out there in malware. We know that's a losing battle. I mean, if we're a winnable battle, Moritz and I would probably form our own company, get some VC funding for millions of dollars, and like do this for a day job. But like, 80% solution again is so good for us. We can save so much time just by using this one tool. That this is what we're going to try to do. Not solve every possible string, but solve the general case. Save some time there. Anything else? Next slide. Download it from here.
Yeah, it's where you can
Give
get
you a
it.
sec to snap it if you want, Snapchat it, Twitter it. All right.
And then we'll...
And we'll turn it over to some questions. So the first hand I saw was up front here, so let me answer your question first. Go ahead. I was using Ubuntu. I statically compiled it using PyInstaller. I expect it to work on most distributions for that standalone binary. Now, it's pure Python, so it should really run on HPUX or any other operating system you want. But the standalone binary, although it's not tested, should run on most Linuxes. If you're having trouble, let us know. We'll build another copy for you. All right, the next one I honestly saw, I think was over on this side. Sure, so there's definitely some interesting things going on in your question there. One is there are cases where this tool cannot work, right? For us to provably extract every string is impossible, right? That's the halting problem. We cannot tell if we've extracted all the strings without executing it to completion. Computer science theory tells us we cannot do it for every possible circumstance, so we're not going to try. We're going to do the most common case. So if there's malware that has a sequence of calls to various different functions that have to be called in a specific order, we can't do that. But most malware authors don't use that technique. They use one of the techniques that we described earlier, macros, C compiler plugins, source code transformation. Now, the other thing that you kind of mentioned was this malware has multiple different DLLs that it loads into memory and maybe delegates to each one. Our program not only runs on executables, EXEs, it'll also run on DLLs. Right? DLLs are composed of functions, basic blocks, instructions. So you pass just a single DLL in, not the whole ecosystem, a single DLL in. It can still do the same analysis. It can still identify decoding routines and extract the strings. So I expect that the tool will probably work for that situation.
I'm just going to switch back to the download link here. So the other one was our contact detail.
Totally, yes. If you can share them with us, we'd love to take a look at them. Contact us after, and we can be careful about them. Or if you have hashes and you're able to put them on VirusTotal for whatever reason, just send us the hash and we can download it from there. But yes, if you find samples that don't work for some reason, we'd like to triage that. We may come back and say, this is too complex, we can't easily do it for you. Or we can say, oh, that was an omission. Let's try to patch it and get it working for you as well. We'd love, if you find samples that don't work, send them our way. We'll fix it for you. Go ahead. Right, so a good question here about what happens if we actually do have a pack sample with UPX or ASPack or one of these other packers. What is this tool going to do? It's not going to work very well. All right. This tool is really only going to work well if we have files that are not already packed, but use just only string obfuscation techniques. Okay, so we're not really able to effectively emulate the unpacking phase and then continue to analyze. But we're strictly dealing with malware that tries to pretend that it's not malicious by not packing itself, but again, hiding those critical resources often in strings. Oh, if you were able to manually unpack it and then dump it from memory, something like that, then you can throw it into the system and it should work just fine. Totally. Good question. I would expect so. Unfortunately, I don't have a large corpus of Linux malware, so if you do, let's chat. All right. Who wants to know more about packing and me to drone on about malware analysis and basic blocks? This guy does. Let's keep going. Sure. Again, lack of malware samples. InfoSec does support analysis of ARM, both from analyzing the code and also the ARM emulation support was recently merged in for some modes, so a lot of this analysis should be able to kind of translate over for ARM binaries. But again, I don't have enough binaries to practice on, so I don't know You probably haven't seen them either. Definitely feasible. I'd love to do that research as well. Definitely. Let me throw it back at the audience. If you have a binary that you expect to be Chinese, what do you do? When you're running strings on it, like what do you do? Is there an extra option you pass to strings to get it to dump Chinese strings or Russian strings or whatever? I'm not familiar with that option. I don't really know how you'd approach it. I think we could find a solution. We could find a way to extract only Chinese strings or only Russian. We might have to have a dictionary in there that has a list of all the valid characters. But off the top of my head, I'm not familiar with a library that already does this, so we'll have to work on that. Yes. Generally. Right. I think that's a great counterpoint. So there would be value to this. Might be doable for sure. That's also a good point. I don't think we're cutting into other people's times yet, so if you have more questions, we'll have to answer them, but also if you need another beer, feel free to grab one, and we'll check in on the next presentation as well. All right, that's it.
Thanks.